Hello and welcome back in Calculus today. Today we will be talking about trig integration. So this comes after integration by parts. Now, this seems kind of like a little bit out of the blue if you specifically look at the type of trig integration that we're going to be doing. But I can assure you that you will definitely see this in the near future because this is more of a stepping stone to something that's going to be a little bit more harder in the later chapter of chapter 7. But anyhow, let's go ahead and get started. So as you can see beneath over here, we're going to be solving for these type of specific integration problems where we have cosine of m to the x times sine of m to the x, and then also tangent of m to the x, and then you have secant of n to the x. So we'll just go ahead and dive straight into it so you can see what I'm talking about. So here's the first example over here. We have the integral of sine of 7 power x and then times cosine of x dx. Now this one is actually pretty straightforward. Hopefully you can see, and the reason for that is, well, one is a one is a derivative of the other. So what that means is you can use a u substitution. Now there aren't a lot of choices to choose from because you can either use u is equal to sine or u is equal to cosine. So the best thing to think about is, okay, well, if I'm going to use u as one function, will du be present over there without any kind of bad residuals? And if the answer is yes, then that means that that's probably your best choice. So let's go ahead and take a quick look at it. I'm probably looking at u is equal to sine of x, because then you can see that du is equal to cosine of x dx. So you can see how this is a perfect substitution then, because du is over there and then u is over here. So as a result, what will happen is you're going to integrate u to the 7th power du. So that's just a regular power rule, which isn't too bad. So it looks like it's going to be 1/8 times u to the 8th power plus c. So your final answer for this one, just substituting it back, is 1/8 multiplied by sine to the 8th power of x, and then we have plus c then. So you can see that, yeah, this is a pretty straightforward example. Now, in the second example, we have something similar, but then the problem is that, well, we don't have just a plain old cosine of x or just a sine of x. So the question is, well, which one do you actually choose? And the simple answer to that is, well, you can choose actually either one. So here, we'll just go ahead and use the same idea then. We're going to go ahead and let u equal to sine of x then, okay? Just the same as the one above it. So then that way du is equal to cosine of x dx. Now, looking at what we have, you can see that the first part over here, we definitely have the integral of u to the 3rd power. But then my problem is that when it comes to du, we have cosine of x dx, and then we also have cosine of 4th power, so that's actually not a good thing. Here, let me just kind of write it out in a form that might be able to see it a little bit better. First, let's see. I'm going to go ahead and put right here the sine of cube x, and then we also have cosine of x dx, right? So that part, you can see that that's equal to u, because this is going to be du over here, and this is actually technically u cubed. Now, taking out what we have already for u and du, what we're left with is that we have cosine of the cube x, and that is where it gets complicated because we don't know what to do with that, or in fact we don't have something nice to actually replace it with. So then that means that this is probably not a good substitution in this case because of this residual part that is leaving us something with that something that's problematic. If it were something like, say, cosine squared, that might be a little bit more usable because then what we could do is change it so that it is use a trig identity to make it so that it's 1 minus sine squared then. So let's go ahead and reevaluate what we're doing, okay? Let me go ahead and do the following this time and switch it, right? So, just trial and error. Now we're going to go ahead and say let u equal to cosine of x then, just swapping things around. So hopefully this time we'll have better luck. So then that means that du is equal to negative sine of x dx. Now, when it comes to replacement, so let's go ahead and write that out. Let's see, u is going to be cosine, so that means we have cosine of 4th to the x, so that's going to be u to the 4th. Now, one of those signs is going to be used for dx part over here, for du over there. So that's going to be negative du because du is equal to negative sine of x dx. what's left is that in the middle, because you extracted out one of the sign, then that means it's going to be sine squared. And we can actually work with that because, as I said, we can go ahead and change that sine squared into 1 minus cosine squared. And as a result, then that's going to be 1 minus u squared then. Okay, so I do actually like that because that one is going to be a good fit for all of this. So we'll go ahead and write it out. Okay, so we're going to say the integral of u to the fourth and then multiply by, remember that sine squared is now going to become 1 minus u squared. And then we also have the negative du over here. So that's what we're going to write right there then. Okay, clean this up a little bit because I don't like the negative. So maybe what we'll have is u to the fourth multiplied by u squared minus 1, just to kind of swap that factor. And if we were to multiply all that out, that's u to the sixth minus u to the fourth, and then we have du. Once again, it's a nice little power rule right here that we can work with. So that's going to be the integral. Oh, sorry, no longer integral because we can actually integrate this. This is going to be 1/7 u to the seventh power minus 1/5 u to the fifth power and then plus c. And finally, we're going to go ahead and plug everything back in. So 1/7 multiplied by cosine to the seventh of x minus 1/5 multiplied by the cosine to the fifth power of x and then plus c then. Okay, so, again, when it comes to trig substitution so far, or trig integration so far, it's just a matter of u substitution. One is the function and then the other one's derivative. There's not a lot of choices. If you try one and it doesn't work, then try the other one. Okay. Now, the two examples that we've looked at so far, both of them have at least one odd exponent. So it kind of works out in this case. But what happens if we have maybe like say both of them are even exponents to, just to see what happens in this scenario then, okay? Well, here, let's just kind of get an idea as to what's going to happen. If we were to use a trig identity, like the one that we just did with 1 plus, oh, sorry, not 1 plus, but 1 is equal to cosine squared plus sine squared. Unfortunately, I don't think it's going to work out too well in this case because look what happens. The cosine, let's go ahead and change that to maybe like say 1 minus sine squared of x. And then we have sine squared of x dx. Now, if you're thinking u is equal to sine of x, that's fine. But the problem is then we don't have du because cosine of x dx is nowhere in this equation. So this, unfortunately, is not going to work out. But it's not to say that we can't do it. It just means that we have to be a little bit more, creative about this. So in this scenario, where if both of them are even exponents, what we can do is we can use a different trig identity. The trig identity we're referring to is the double angle formula. Now, I'm going to go ahead and write it on the side just in case you forgot it. So cosine of x squared is going to be equal to the following. So cosine of x squared, or cosine squared x, is equal to 1/2 multiplied by 1 plus cosine of 2x. Whereas sine squared of x is equal to 1/2 multiplied by 1 minus cosine of 2x. And if you're wondering, well, why would I want to use the double angle formula? Well, the reason is you're taking that exponent and changing it into a composite, which we can actually easily solve for using the chain rule in this case. Okay, so here, let me just go ahead and plug it in so you can see what I'm talking about. So both of these guys, I'm going to go ahead and plug it in, and that way we can diminish our exponents. We're going to have 1/2 multiplied by 1 plus cosine of 2x, and then we have 1/2 multiplied by 1 minus cosine of 2x. And that looks like it's a pretty nice setup because I can take the 1/4 on the outside, and on the inside, that looks like a difference of square, so that's going to be 1 minus cosine squared of 2x and then dx. So the nice thing here is that we no longer are dealing with two different trig functions, but we're dealing with one. But nonetheless, this still gets us to the point where we're saying, okay, well, we still have, if I let u equal to cosine of 2x, du is not there. But that's okay. What we can do is repeat the procedure once again using the double angle formula. If we do so, then what we're going to have now is 1/4 and then integral. Now this guy right here, that's going to be used with this guy over here. So that looks like the following now, and hopefully you can catch up. 1 minus 1/2 multiplied by 1 plus cosine of 4x, okay, and then dx. So notice once again, I use the double angle formula to diminish my exponent. So then that way we have something that is inside of a composite function with 4x. Okay, let's see. That looks like it's, not too bad. So let's kind of finish this off. So 1/4, the integral for the inside part looks like it's going to be 1 minus 1/2. So that's going to be 1/2. And then minus 1/2 times the cosine of 4x, and then we have dx. So let's see, that is going to be equal to 1/4, and let's go ahead and integrate this. 1/2 raised to the, 1/2 times x, and then we have cosine is our derivative, so that means that the antiderivative is going to be sine then. So there's going to be a 1/2, this antiderivative, which is sine to the 4x, and I'm going to divide by 4 because of the chain rule. And then all of that is going to be plus c. So finally, we'll just go ahead and multiply everything out. So it looks like my answer is going to be 1/8, and then minus 1 over, 4 times 4 times 2, that's equal to 32, and then that's going to be sine of 4x, and then plus c then, okay? So there you go. All right, so that was the difficult one, so hopefully it wasn't too bad. Now, let's see. What happens if you have just like a cosine of to the 4th power of x, where sine is no longer present? Well, you can do exactly the same thing, because using this double angle formula, what we can do is we can diminish that exponent of 4 into something smaller that we can manage. So let's see, that's going to be the integral of, let's see, well, let me just kind of write it in this form so you can see it a little bit better. Cosine, right here. So the integral of cosine squared x times cosine squared x, okay? And then now we'll go ahead and use the double angle formula. So there's going to be a 1/2 times the cosine of 2x, and then we have plus 1. And then we also have the other 1/2 multiplied by cosine of 2x, and then we also have another plus 1 dx. Okay, so very similar to what we just did. The 1/4 I'm going to go ahead and take outside. The inside, that is going to be a perfect square, which we're going to have to multiply out. So let's see, this guy multiplied by this guy, that's 1 plus 2 cosine of 2x, and then plus cosine squared of 2x squared. So all of that is dx. Now, I can integrate the 1, no problem. I can integrate the 2 cosine of 2x, no problem. This guy is going to be a problem, so we're going to have to do this one more time with a double angle formula. So 1/4 integral of 1 plus 2 cosine of 2x, and then plus 1/2 multiplied by 1 plus cosine of 4x, just like last time, okay? So this is where, all those time that you did trig identity in your pre-calc class comes in handy. Hopefully you didn't fall asleep or kind of forgot about it over the years. So let's clean up the algebra, and then we'll go ahead and integrate that. So 1/4 integral, we have 1 plus 2 cosine of 2x, and then plus 1/2, and then plus 1/2 cosine of 4x. Let's see, taking the antiderivative, the 1/4, I'll keep it as is. The 1 and the 1/2 right here, that's going to give you 3/2, and then that's going to be x. And then plus this part right here, the antiderivative, is sine of 2x. The 2 and the 1/2 that it's going to produce is going to cancel out, so that's the nice part, so that's going to be gone. And then we also have this last part right here, where the antiderivative is going to be sine again of 4x, and then we're going to produce a 1/4, and then also we have the 1/2, and then all of that plus c. So it looks like my final answer is 3 divided by 8x, and then plus 1/4 times the sine of 2x, and then plus 1 over 32 times the sine of 4x, and then quantity plus c. So there's your nasty antiderivative. Okay. All right, so I think we've done enough with the cosines and sines, but here, just as a general rule, if both exponents are even, then use a double angle formula to help you out with it, okay? So now let's go ahead and look at what happens when you have tangent and secant, because, this one is going to be pretty similar to what we just did. Now, the reason why I say it's similar is that tangent and secant, well, one is a derivative of the other. So just like with sine and cosine, you just have to figure out which one is which one is u, which one is going to be du in this case. So here, right off the bat, I am going to look at maybe like say u is equal to the tangent of x. And so du right here will then be equal to the secant squared of x dx. So that worked out nicely in this case because you can see where u goes in and du goes in. So this guy right here, that's u to the third. This guy right here, that's going to be du. Now, had you have done it the other way around, if you said that u is equal to secant of x, then that means that du is going to be equal to secant of x tangent of x dx. And unfortunately, that comes out to be a lot messier because we're going to have a lot of residual parts, which is what we're trying to avoid. So we're probably not going to use that case then. Okay, if you see just secant squared x, that's probably going to be an indication that that's going to be du. All right, so that now gives me the integral of u cubed du. So that's 1/4 u to the fourth plus c. So we replace it back, 1/4 times the tangent to the fourth x and then plus c, and that's going to be our antiderivative. Okay, let's look at a different case. What if we have cosecant and cotangent? Well, same idea, right? One is the derivative of the other, so you just have to figure out which one should be which. If I let u equal to cotangent of x, then du is equal to cosecant squared of x dx. Now, that unfortunately is not nice because you can see we have cosecant of cube x, and that means that we have an extra cosecant that we can't deal with. So this would probably not be ideal. So then try the other way around. Oh, sorry, there's a negative too, and also just in case that matters, which it does. So let's say now this time let u equal to cosecant of x. So then du is going to be equal to negative cosecant of x times the cotangent of x dx. If I do that, it looks like it works out nicely because let's see, if I were to rewrite this just like we did in the last examples, this is going to be cosecant squared of x times cosecant of x and then times the cotangent of x dx. So here you can clearly see that this is going to be negative du. This is going to be then equal to u squared, and yeah, I can definitely work with that. Okay, so if that's my setup then that means the antiderivative is 1/3 negative u cubed and then plus c. So going back and plugging in what we have, so 1/3 times cosecant cube of x and then plus c then. And that's your antiderivative. Okay, so after a while, I think you get the idea as to like, what you're really doing, because a lot of these times you're really just using what's u and what's du. And if that doesn't work out, then that's where the identities come in then. All right, let's keep going. Here in this, I think the last example over here, what if we have tangent cube and secant cube then? Okay, so let's see. We can go ahead and say u is equal to tangent of x, and then so du is equal to secant squared of x dx. And you can see that that's now a bad thing because just like before, we're left with an extra secant, so that's not going to be a good substitution. So with that out of the way, we will now go ahead and use u is equal to secant of x. Du would then be equal to the tangent of x times secant of x dx. So if I go to my original problem, I definitely see du there because if I rewrite this, this can be rewritten as the tangent squared of x times the secant squared of x multiplied by secant of x times the tangent of x dx. So that part right there, that's going to be du, which is good. U is going to be this part right here, which is u squared. So the question is, what do we do with this guy? Well, I think you guys get an idea of what's going to happen then. Your identity in this case, right, hopefully you didn't forget, is 1 plus tangent squared of x is equal to secant squared of x. So if I were to rewrite it, then that means that tangent squared is equal to secant squared of x minus 1. So my question mark over here is then going to be replaced with, looks like it's u squared minus 1 then. Okay, so let's go ahead and write that. The integral of u squared minus 1 multiplied by u squared du. Multiply this out using the power rule. So u to the fourth minus u squared du. Antiderivative, 1/5 u to the fifth minus 1/3 u to the third, and then plus c. Replacing back everything, so the final answer is 1/5 times secant to the fifth x minus 1/3 times secant to the cube x, and then plus c then. All right, well, there you go. Thank you so much for watching. Hopefully this was insightful. I will see you guys next time. Goodbye.